Thank you for joining us at Microsoft Research Summit 2021. My name is Andrey Kolobov, and in the next few minutes, together with my colleague Ching-An Cheng, I'm going to talk about Project Dexter, MSR's recent effort that focuses on machine learning and decision-making for dexterous robotic manipulation. This is joint work with Mihai Jalabeanu, Vibhav Vinit, Sheetal Shah, and other collaborators. The motivation for our project is the recent trend in robotic manipulation hardware towards becoming increasingly versatile. Some of the hardware manipulators available on the market, such as the shadow hand that you see in this image, are physically capable of performing many of the things that a human hand is capable of, from screwing in a lamp bulb to picking fruit or vegetables. But the reality is that writing software that specializes this hardware to any given task is extremely tricky. As a case in point, it took about 20 experts from OpenAI, some of the top roboticists in the world, 2 years of work and about 13,000 years of simulation to train a physical shadow hand for a single complex task, in this case, assembling a Rubik's Cube, by following a known algorithm. And the success rate of the resulting policy was only 65%. So the goal of our project is to enable training robotic manipulation systems for real-world tasks at a cost that is practical in expertise, time, compute, and robustness. At Microsoft, we have a number of internal scenarios that we would like to automate or semi-automate with robotic manipulation. So they mostly have to do with Azure data center maintenance tasks, such as recycling hard drives, flipping circuit breaker switches, such as in this scripted policy that's shown in the video. And these scenarios serve as our guiding star and sanity checks, but I'd like to emphasize that our goal in this project is not to solve any specific robotic manipulation scenario, but rather to produce machine learning methods and tools based on these methods to enable robotic manipulation practitioners to easily solve their own scenarios of interest. The team working on Project Dexter comprises people from several MSR groups, vision group, engineering group, and the reinforcement learning group. But we also have collaborators within MSR, beyond MSR, within Microsoft, and beyond Microsoft as well. A few words about our general approach. So the main premise of our approach is the observation that the amount of data that we can realistically collect for training a robotic manipulation system for a given task is typically much lower than the amount of data that modern imitation learning and reinforcement learning algorithms need in environments with high dimensional observations to produce a good policy. And the second premise is that simulation, which is a way of getting a lot of data in many scenarios, including robotic scenarios in general, specifically in robotic manipulation, often falls short. Simulations are not able to model some of the critical aspects of robotic manipulation. And as a result, they cannot be the sole source of data and not even the main source of data for us. Our key observation is that although we can only collect limited amounts of data for a given for the task that we want to solve, we do typically have a lot of data about tasks, about other tasks, and collected from other systems. This data can come in the form of videos recorded of a different robotic manipulator, or even a person trying to accomplish a manipulation task. And some of this data can come with annotated actions, which are recorded on our own system or on an identical system performing different tasks in different circumstances. Although none of this data is directly relevant to the target task, our hypothesis in this project is that it gives us a way to learn a very important meta skill, if you will, that generalizes across a wide range of robotic manipulation tasks. And the skill is taking the high dimension observation stream of a robotic manipulation system, such as a stream from its video cameras and sensors, and distilling it into features that are relevant for decision making in that scenario. And one major part of our agenda is devising machine learning methods construed broadly, from unsupervised machine learning methods to lifelong learning and reinforcement learning, that would allow us to learn this model for extracting a compact world representation from high dimensional observations. Our other hypothesis is that a representation like this, combined with a small, affordable amount of on-task, on-system data, will allow us to learn a robust, high-quality policy for the target task using specially modified or newly invented reinforcement learning and imitation learning techniques. And the other major part of our research agenda is coming up with such decision-making and machine learning techniques. Here are some examples of problems that we are considering in this project. One question we're trying to answer is how to combine video-only training data, essentially a video recording of an agent trying to accomplish a manipulation task, with recordings of trajectories that come not only with video frames but also with actions that the agent performs. Here we're exploring, the solution we're exploring is pre-training a transformer-based architecture using novel auxiliary losses. Another question we are thinking about is how to train a robotic manipulation system to gather data for the target task on its own, just after seeing data from performing other tasks. The motivation here is that although we cannot collect large amounts of high quality, demonstration quality data for the target task, we may be able to collect construct a reasonably good policy for collecting data. And this is a direction that we are pursuing in collaboration with University of California, Berkeley's Robotic AI and Learning Lab. The third question that we are trying to address right now, which is highly related to the previous question, is how do we learn from autonomously collected offline data for the target task. As I just mentioned, we don't expect this data to be of high quality, so we cannot use it for demonstrations. And instead, we're exploring robust offline reinforcement learning approaches that my colleague Ching-An is going to go into in more detail in the next few minutes.
One of our current research focuses on designing robust offline RL techniques that can leverage any existing data to improve a robot's performance without making strong assumptions on the data quality or quantity. In a high level, our approach is to compute policies that are consistent with the given data set and are robust to the unknowns in the environment. Importantly, we don't want this policy to be unnecessarily cautious, otherwise the robot behaves slowly or very suboptimally. Let's take the problem of grocery unpacking as an example. Here the robot maybe have experiences of manipulating similar but different produces and daily objects in the lab environment. But when unpacking a real grocery bag, the robot faces several challenges it doesn't have in the lab, such as the objects now are in the grocery bag are only partially observable, and there may be some fragile objects such as eggs. And ideally, we wish the robot to be robust to these uncertainties and have a policy that can balance unpacking speed and not breaking fragile objects. In this year's new resubmission, we propose a novel algorithm called pessimistic self-policy iteration, or PSPI for short, that can exactly do that. PSPI works by alternating a pessimistic policy evaluation step and a self-policy improvement step. In the policy evaluation step, it computes a policy's value function estimate that is pessimistic at the initial state and is consistent with offline data. And then later on in the policy improvement step, it computes a policy that can robustly improve a policy's performance while considering the worst-case scenario. In this framework, we can encode a problem structure as a function prior in the policy evaluation steps, such as using the representation learning technique that we talked about earlier, and doing so can prevent the robot from being unnecessarily conservative. We theoretically prove that this framework is doubly robust in that either good data collection policy or good representation learning is sufficient to output a policy that is robust and has good performance. And currently, we are working toward training deeper model with this PSPI framework and applying it in the real robot experiments.
So in conclusion, Project Dexter is a project with deeply practical motivation, but its research agenda is asking us to tackle some of the core research challenges and answer some of the core questions in AI. And in doing so, we're very much open to external collaborations. Thank you for your attention.